everyone. Welcome back to the Population Ecology Lecture Series. Today's lecture is going to be about some simple predator-prey models. And before we get into it, I wanted to talk a little bit about why we use these simple models. Because in reality, what we're looking at is these pairwise associations that are embedded in these multi-species communities. And so some predictions we want to make need to come out of food web theory, but it's really important that these pairwise associations are understood, because when we have predictions from pairwise models, we can then go out and test those predictions in the field and see when they fail and try to understand what complexity is important. So what aspect of that complexity matters is going to be revealed through testing these simple predictions. So I think Rockwood did a really great job of kind of laying out caveats associated with using predator-prey Lotka-Volterra style dynamic models. And so I'm just going to go over his and then add a couple extras that I think we've talked about in the past in this class, and I just want us to make sure that we're still aware. So, number one, prey often escape predators through refugia, or any kind of refuges. So if they can hide from predators, they often escape, and that's not something that's accounted for in the models. Secondly, predation is almost always non-random. In fact, the importance of predation for structuring communities and having effects on ecosystem processes really depend on the fact that there is selective predation. So we have some systems where predators will attack the most common prey, or the one that they first come into contact with, or some that have certain traits, and those end up having cascading consequences for entire communities and ecosystems. But that's not accounted for in these models, which are basically looking at encounter rates as being a random determinant of predator-prey dynamics. Secondly, growth rates differ between predators and prey. And basically those differences in growth rate can have big consequences, and it's not something that is accounted for in these models. Third, generalist predators are really common. So is prey switching. So what does that mean? Well, switches. What it means is in these models where we're looking at pairwise associations, we assume that if one particular prey species goes away, then the predator has nothing to eat. And that's an assumption that's usually not borne out in natural communities, because it's really uncommon to have predators that only have one prey that they feed upon. Prey switching is really important, in part because of that point I just made about how selective predation on the most common species can keep any one prey species from becoming overdominant in a community and competitively excluding others. So empirically, predator populations are more stable than prey populations. And so we know that first point, or that previous point, number 4, that prey switching happens, in part explains that, but it doesn't completely explain it. So we don't have a great understanding of why prey populations fluctuate a lot more than predator populations. But what we do know is that our models, our really simple Locke-Volterra style models, don't account for those differences. Okay, so I'm going to erase this so I can give you the next 5 caveats. And, as I'm doing that, I want you guys to think about, what kind of dynamics you expect from communities and why it might be important to look at just some pairs of species to make predictions. Okay, next, predator populations can be limited by carrying capacity. Due to ecological conditions that are unrelated to prey. So this essentially means if we're looking at density-dependent interactions, when we think about predators, we often think about prey as a resource, but that's not their only resource. So you could have things like space or nesting availability be really important. You could have other considerations due to parental care be really important. There's a lot of different factors that are related to carrying capacity but unrelated to prey availability. And these models assume that prey availability is the main thing. And, it's not a terrible assumption because that is a major resource affecting predators. It's just not the only one. Another thing to keep in mind, and we've said this for a lot of the models we've talked about this semester, is that density-independent mortality from things like environmental stochasticity are ignored in these models. And so some more recent models have added in a kind of random factor to try to account for this. But in general, just understanding the models we're going to go over, what we're going to see in populace, that aspect of their ecology is ignored. Okay, so the last one that Rockwood talks about is that there can be more than one equilibrium for predators and prey. But these models they usually just have one. So they're simple models, and they're not going to account for some environmental factors, some ecological conditions that may lead to more than one stable equilibrium. So this is one case where these models are really effectively used. So if we expect a stable equilibrium to be at a certain point, and instead we see it in a completely different point, that's where we can start asking about what aspects of the complexity that these models are assuming doesn't exist, what aspect of that complexity is driving that new equilibrium point, given that it's stable. Okay, so I have two more, and it's just things we've talked about already that Rockwood didn't include. First is what we know from metapopulation models and let's just stick with metapopulation models in this class. The immigration and emigration can be really important, and so considering spatial complexity is an important thing to do, and understanding dispersal between among different populations can be important for these dynamics. So you could have rescue effects for some prey, and you could have stabilizing effects for some predators through those dynamics. And the final one is all individuals are treated equally in the model. So any intra-specific variation in the ability to evade predators or capture prey, or any real intra-specific level trait are basically ignored in these models, and they can also be really important. But then we get to the point of the complexity required to make an individual-based model makes those models less applicable more generally to all sorts of different species. And so these are always going to be trade-offs, and I think if you're interested in understanding this complexity of ecological communities, you really need to understand the mechanisms happening at the population level to then expand out to the community level. Otherwise, just looking at food web dynamics doesn't give you the kind of predictive ability that you need to be able to understand what's going to happen in response to future events, or even just future change in population size. And so I think I'll just end this introduction by telling you to consider, as you're going through these population models, how are they going to scale up to communities? When you're starting to read the community ecology literature and you start getting into papers that are talking about food webs, which we'll have one later in this week's class, I want you to think about what that means for these pairwise interactions and how they could inform our understanding of those food web models, because they do go hand in hand in a really quite exciting way. And so with that, that's your introduction to this topic, and the next lecture will be actually building those mathematical models.